Astronomers have discovered a record-breaking black hole in the Milky Way galaxy, and it's surprisingly close to us. This black hole has a mass 33 times greater than our Sun, setting a new record for the largest black hole of stellar origin found in our galaxy. It's located around 1900 light-years away, making it the second nearest stellar mass black hole to Earth. This discovery was made possible through 11 years of data collected by the Gaia Mission, an astronomical survey conducted by the European Space Agency. The black hole is a companion to a Sun-like star in a binary system named Gaia BH3. The immense mass of this black hole challenges what scientists currently understand about how stars evolve and die to become black holes. Usually, the process involves a star burning out and collapsing under its own gravity, but such a massive black hole suggests something is missing in our understanding of this phenomenon. Moreover, there's speculation that Gaia BH3 could be part of a three-body system, meaning there might be another celestial body involved, influencing the dynamics of the system. This idea comes from how the black hole and its companion star interact, suggesting there could be gravitational influences from another object nearby, adding an exciting layer of mystery to this system. So, how was this black hole discovered in the first place? How could this discovery open Pandora's box in the field of astrophysics? Finally, and most importantly, what does the discovery of a black hole in our cosmic backyard mean for astronomers? The story begins with the breakthrough detection of gravitational waves in 2015, confirming a century-old prediction by Albert Einstein in his general theory of relativity. Gravitational waves are ripples in the fabric of space-time, caused by some of the most violent and energetic mergers in the universe. These waves are crucial because they provide information about the nature of gravity that can't be obtained through traditional electromagnetic observations like light. Following this discovery, scientists began detecting gravitational waves from numerous black hole mergers in distant galaxies. When they determined the masses of the merging black holes after analyzing the gravitational waves, they noticed something strange. The black holes involved in mergers in distant galaxies were much more massive than those typically found in our galaxy. Observing the discrepancies in the masses of black holes within our galaxy was intriguing compared to those detected through gravitational waves in other galaxies. One reason could be the method used in the two cases. Most of the Milky Way's known black holes have been identified through emissions from X-ray binaries. These are systems where black holes pull in material from a companion star, causing the material to heat up and emit X-rays. However, they represent a small portion of the black holes in our galaxy. Many black holes in the Milky Way remain undetected because they do not interact with other stars in a way that produces noticeable emissions. This invisibility is challenging because it limits our understanding of the full range of black hole masses in our galaxy. So the only way to explore this discrepancy was to find silent, dormant black holes in our galaxy that were simply minding their own business. Searching for these black holes is like finding a needle in a cosmic haystack, requiring astronomers to sift through vast amounts of data and deal with information overload. When it comes to browsing the web, you don't have to face such a daunting task. Thanks to Opera browser's AI, Aria, navigating the internet is effortless. Instead of surfing through countless web pages, Aria, conveniently located in the sidebar, provides clear and instant answers. It connects you to real-time information and generates content based on your ideas with just a few clicks. You can explore and translate any highlighted text on a page with Aria. And when you need a bit more organization, Tab Island comes to the rescue. You can effortlessly group your tabs by context, news, websites, workspace, social media, and save space by collapsing islands. This feature makes your browsing experience both efficient and enjoyable, ensuring you stay focused on what matters most. Plus, the built-in VPN offers private browsing, hiding your location and keeping your activity secure without logging any information. Another feature I adore is Opera's Battery Saver. It lets me browse for up to an hour longer without needing any extensions, and takes just a single click to activate. This built-in feature ensures I can keep exploring the wonders of the universe, even when I'm away from a power source. So click the link in the description to download Opera for free and transform your internet browsing into a seamless experience. Now back to our cosmic quest. This is where the Gaia mission comes into the picture. Its main aim is to create a detailed 3D map of our galaxy by accurately measuring the positions, distances, and movement of stars. Although Gaia can't directly detect dormant black holes, it has a unique way of uncovering their presence. Gaia observes stars over long periods, and by doing so, it can detect subtle changes in their movements. Normally, a single star moves in a predictable, straightforward path. However, in a binary system, where a star orbits with another object, its movement can show variations or a wobbling effect. This wobbling can indicate the presence of a second object, even if that object is a dark, invisible mass like a dormant black hole. So by meticulously analyzing these motions, Gaia can hint at the existence of a high-mass, invisible companion, potentially a black hole, even without directly observing it. In the constellation of Aquila, astronomers noticed something interesting using data from the Gaia mission. They saw a star wobbling and moving in a way that suggested a massive, invisible object was affecting it. This star and its hidden companion are in a wide orbit around each other, taking about 11.6 years to complete one full orbit. The distance between them changes a lot during their orbit. At their closest, they are 4.5 times the distance from the Earth to the Sun. For comparison, that's slightly less than the distance from the Sun to Jupiter. At their farthest, they are 29 times the distance from the Earth to the Sun, which is almost as far as the distance from the Sun to Neptune. Both the star and dark object orbit their common center of mass. The orbit of the dark object is roughly the size of the orbit of Mercury. By analyzing the precise movements, distances, and positions of the star relative to the system's center of mass, astronomers estimated that the invisible object has a mass of about 32.7 times that of the Sun, while the visible star has less than one solar mass. Considering the TOV limit, which is the theoretical maximum mass a neutron star can hold, approximately 2.17 times the mass of the Sun. Even if there were 15 neutron stars combined, which is a highly improbable scenario, their mass would still fall short of the calculated 33 solar masses for the dark object. Astronomers concluded that the invisible object was likely a black hole. This conclusion is supported by the object's mass being well beyond the upper limit for neutron stars, making a black hole the simplest and most plausible explanation for the observed data. Astronomers analyzed the Gaia BH3 system over a period of 11 years. The star's motion within this system was meticulously tracked against the sky, and the observations clearly aligned with the predictions of a binary star system model marked in blue rather than those of a single star marked in red. The observations made by Gaia are indicated by white dots on the graph. An animation accompanying this study illustrates the orbit of the star and the black hole in Gaia BH3 from 2013 to 2024. In this visualization, the star's orbit, depicted in yellow, follows a blue ellipse, while the much smaller orbit of the black hole, shown in black, follows a tiny red ellipse. Both objects are seen orbiting around a common center of mass. Another panel in the animation displays the radial velocity of the star as it moves along its orbit, further detailing the dynamics within this binary system. Before the Gaia mission, no dormant black holes had been discovered. Gaia, however, has successfully identified several, with Gaia BH1 and Gaia BH2 found in the past 2 years, and Gaia BH3 more recently. Among these discoveries, Gaia BH3 is particularly notable for its distinct characteristics. An interesting aspect of Gaia BH3 is its orbit compared to earlier finds. This animation comparing the orbits of the black holes and their companion stars places these orbits in context by projecting them onto a scale with the solar system. Using the Sun as the reference point, This visualization clearly shows that the star in the Gaia BH3 system is in a much wider orbit around their mutual center of mass than those in the Gaia BH1 and BH2 systems. The wider orbit in Gaia BH3 is significant because such orbits are typically harder to detect and require longer observation periods to confirm. This makes Gaia BH3 an outlier, not just in terms of its orbital characteristics, but also in terms of the mass and the orbital period. The discovery of the Gaia BH3 marks a significant milestone in astronomy, primarily because it hosts the most massive stellar black hole ever identified in the Milky Way galaxy. This black hole is also remarkably close to Earth, being the second closest known. Its mass places it within the range of black holes typically detected through gravitational waves, highlighting the importance of this discovery. However, the presence of such a massive black hole in a wide binary system raises profound questions about the current understanding of stellar evolution. Two key questions challenge astrophysicists. How did such a wide binary system form? And how did the black hole come into existence? It's hard to explain how this black hole formed because it's far from its companion star, about 1,000 times the radius of the Sun. This large gap doesn't fit our current understanding of how black holes form, especially if the black hole came from a massive star, about 150 times the mass of our Sun. Furthermore, the system exhibits a retrograde orbit, suggesting it moves in the opposite direction compared to most stars in our galaxy. This unusual movement might indicate that Gaia BH3 originated from a merger event, possibly with a globular cluster, which is a tightly packed group of stars. The system's formation could have involved a dynamic exchange where the black hole captured its companion star in a dense stellar environment. Additionally, the star in the Gaia BH3 system has a chemical profile similar to that of stars in the ED2 group. Scientists think the ED2 group was formed when a globular cluster tore apart and merged with our galaxy. There's also a tantalizing possibility that the observed star orbits not one, but a pair of black holes, making Gaia BH3 potentially the most exotic three-body system in the universe. This hypothesis is still under investigation, and if it's confirmed, it would further underscore the complexity and dynamic nature of celestial phenomena. Thank you for watching, and a special thanks to Opera for sponsoring this video. Make sure to download Opera using the link in the description and discover a faster, safer, and smarter way to browse the internet.